Hey everyone, in this video we're going to look at generating the equations of motion for a pendulum. Now, when we say equations of motion, recall that what we're talking about is the Newton-Euler equation. So Newton's second law, sum of forces, is the change in linear momentum, and then Euler's second law for center of mass is going to be sum of moments is change in angular momentum. Now, we're going to look at this system. There's only the one rigid body, so we're going to call this body A with center of mass point A. So we can say the sum of forces on A is the change in linear momentum of A. We're going to look at sum of forces, sum of moments on A about A. So there we're looking at the change in linear momentum of A about A. And then we're also going to do sum of moments on A about N, and that's going to be ddt of HA about N, and then plus dot, 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 because there's some other terms in there. These other terms, go back and watch the video, Euler's second law, part 3. Now, the reason I want to do it both of these ways, doing sum of moments about A and sum of moments about N being the pin joint, is just to prove that regardless of where you take your moments, if you do it correctly, you get the same answer. And there are times when it's actually easier to take your moments about another point other than the center of mass. Now, in order to do all of this, what's our approach? We want to generate every part of those equations and then put them together. So we need to do, let's say, kinematics. So the kinematics is going to give us our accelerations. So VA dot and omega NA dot. Next, we need to consider our momentum terms. So combining that with our accelerations, really here we're just talking about the mass and the inertia. And when we go to take the moments about a different point, we're also going to have to do parallel axis theorem. Next, we need to do free body diagrams. We need to do the sum of forces and sum of moments equations. We need to combine these things into the Newton-Euler equations, and we need to make sure that all of the unknown, so the unknowns in this case are going to be the reaction forces, all of our unknowns are eliminated. And we might not do all of these things in exactly this order. For example, the momentum terms, we can, these are basically just considerations. So let's start with number 1, and let's knock out the kinematics for this. We already have the points labeled on the diagram. We still need frames. So A frame here is the XA, and YA, we need an inertial frame, XN, YN. Let's do position vectors. So the position vector from N to A, we need some distance. Let's call that L. L in the X had a direction, and I'm just going to do a fast rotation from N to A. This is a rotation about a shared Z-axis, and the angle is theta. We know how to formally define these rotations by now. We can take derivatives. Let's do the angular stuff first. So omega into A, this is going to be theta dot ZA. And omega in A dot is theta double dot ZA. Next, linear. So linear velocity, ddt of P and A, that's going to be L theta dot y hat A, and VA dot is L theta double dot y hat A minus L theta dot squared XA. At this point, you should be more than comfortable doing these things and doing them quickly. All right, with this done, next let's actually do the free body diagram next. Our free body diagram, it's just the one body. So let's put it right here. What's acting on this body? Well, gravity, MAG. There is a set of reaction forces at the pin joint at point N. Now, there's only the one body in this problem. We could put the reaction forces in any frame we want. We can put them in the N frame or we can put them in the A frame. In this problem, because there's just the one body, I think it's actually easier to put the reaction forces in the body frame. So let's say that there is, let's put them aligned with the A frame. So there is a R1X in the X hat A direction. There's R1Y in the Y hat A direction. Again, we could have done this in the inertial frame, and if we do it correctly, we get the same answer regardless. What else is acting? We could model some kind of friction. Let's also, though, let's put a external force, some external torque tau. So let's say that maybe it's an electric motor at point N that is causing this pendulum to spin. It's generating some moment, some torque. This looks good for the free body diagram. Next, let's write our sum of forces and sum of moments equations. So the sum of forces on A, here they are, minus MAG, that's in the Y hat N direction. We have plus R1X, that's X hat A, plus R1Y, Y hat A. Yeah, just the three. Yeah, okay. I'm just gonna bring this one up then. It'll fit. There we go. Next, we said that we wanted to approach Euler's second law twice. We're going to do sum of moments about center of mass, and we're going to do sum of moments about the pin joint, which means we need to write two different equations. We need to do sum of moments on A about A, and we'll come back and we'll do sum of moments on A about N. Now, if we're taking the sum of moments on A about A, so we're taking the moments at the center of mass. Well, the gravity acts through the center of mass, so that creates no moment. We do have the moment created by these reaction forces. We also have this external torque tau. So let's just bring down tau. There we go. And we need the moment generated by those. So that's the position vector from A to N cross R1X, X hat A, plus R1Y, Y hat A. This position vector from A to N, this is minus L X hat A. Now, because we did our reaction forces in the body frame, this is XA and this is XA. If this were XN and this were YN, this position vector would still be in the A frame and we'd have to do some conversion. Either this position vector or these forces would have to change frames. As it is, the X hat A cross X hat A is 0, and what we're left with is XA cross YA yields positive Z. There's a negative in front, so this becomes negative L R1Y in the ZA direction. There we are. Now, can we confirm these just by observation, just by looking at the diagram? Well, if we, clearly we chose a positive moment for the torque, so that's generating a positive spin. If we assume that the value of R1Y is positive, of course L is a positive, it's just a scalar distance. If we assume that R1Y is positive and it is acting in that direction, then in this free body diagram we can see that this force R1Y would create a negative moment. It would make this rod want to spin in a negative direction, hence the negative sign. All right, Write these both down, keep those, and let's do that other sum of moments equation. So sum of moments on A about N. Now this time, if we take the moments about N, the reaction forces are acting at point N. So now the reaction forces create no moment, but we do have the moment from gravity now. So let's bring down the torque. So tau ZA. Next. Now we're taking the moments about N, so we need the position vector from N to A cross gravity term minus MAG y hat N. And this position vector from A to N, we know this is L x hat A. This time we can see that we have a problem with frames. So we have to either convert the position vector into the end frame, or we convert the gravity into the end frame. Go back to our definitions for the rotation of A. We already have it defined. X at A equals something, so let's go ahead and do that. So equal, bring down the torque, ZA, plus. The position vector is L times cosine x hat N plus sine theta y hat N cross minus MAG y hat N. So what is this going to give us? Well, now you can see that the y hat N and the y hat N, that's going to be 0. We're going to be left with L cosine theta, and then x cross y makes positive z, and then there's a negative sign. So this is negative L cosine theta MAG z hat A. There's the answer. So you take care of this cross product, this is what you're going to get on top. We could also check units on that if we need to. The units of torque are Newton meters. Here's a meter, here's a kilogram, here's a meter per second squared. Kilogram meter per second squared is going to be your Newton, so Newton meter. Now let's see if this makes sense. Again, the torque is generating a positive moment, so we want to so that would create a positive spin. And about this pin joint, if this object were floating in space and the gravity created a moment, it would want to make this spin in a negative direction, right? It would create a negative moment about it. So negative cosine theta. Now the change in theta would actually generate, what if this thing moved into a different quadrant? So if it were in a different quadrant, and gravity were pulling it down now, well now that's a positive moment. So we can see that cosine theta is going to change signs as the orientation of the pendulum changes. And that's the sign change here is going to determine whether it's positive or negative moments. Good. Next, let's write this one down and keep it. Next, let's talk about putting these things together. I've rewritten the sum of forces and the sum of moments about the center of mass A. Let's put all of this together now and talk about the equation of motion for this body, and we're going to take the moments about A. Now, we could construct Newton's second law, we could construct Euler's second law. Consider though, which one do we need? Which one is priority? Where should we start? Well, what is the generalized coordinate for this problem? The generalized coordinate was theta, and there's only one degree of freedom. So we know there's only one generalized velocity, and there's only one generalized acceleration, theta double dot. So from the equations of motion, we need to solve for theta double dot. That's the goal, to solve for the acceleration. Well, which one of these equations, Newton's second law or Euler's second law, is going to give us the theta double dot? Clearly Euler's. So let's start with Euler's second law. The sum of moments on A about A, this is going to equal ddt of h A about A. We know that this is IAA times omega NA, and we can expand this derivative. We know that when you're taking the moments about the center of mass, this equation becomes IAA omega NA dot plus omega NA cross IAA omega NA. So what is IAA for this problem? Well, we're looking at a rod, and we're going to say that this rod is symmetric. So we already know that we're going to treat these off diagonal terms like zeros. And since it's a rod, it is the long axis is the x-axis. So that one's going to have some small, negligible amount of inertia about that axis. And then for now, we can just write this as IYY, IZZ. We can do the same thing with the delta. That's the IXX. Now for this rod, if we wanted, we could go online, we could look up the equations for this. IZZ and the IYY, this is going to end up being 1 over 12 MA. The total length is 2L, so 2L squared. That would be the inertia specific term. What I'm going to do for right now is I'm just going to leave this as IZZ, and we can come back at the end and we can do this replacement on the final equations. Since we're rotating about a single axis, since this is a simple rotation about the Z, and this is a symmetric inertia matrix diagonal only, then you can go ahead and work out this linear algebra. This is going to equal 0 for this problem. So what's left? We have our sum of moments equation. I'm just going to bring this down. We've got tau minus L R1Y. This was ZA, and this is equal to the IAA times omega NA dot. Now, omega NA dot, it's 0, 0 theta double dot. Because again, simple rotation about the shared z-axis. The left-hand side I've written is just the vector. The IAA, we know that this is a 3x3 matrix, or dyadic, however you want to think of it. And then the angular acceleration is a 3x1 vector. When you multiply these two together, what you're going to get is that IZZ term from the bottom right corner multiplied by the scalar theta double dot, and this is still vector, so IZZ theta double dot ZA. So let's just clean this up a little bit. And I'm just going to write it now. I'm going to drop these ZA terms. So as a scalar equation, we have tau minus L R1Y equals IZZ theta double dot. Now, are we done? No, we're actually not done, because remember the final step when we mapped out our plan. The final step was we had to eliminate unknowns, and we don't know what R1Y is. In fact, R1Y is always changing. As this pendulum rotates, the instantaneous value of R1Y is going to always be changing. So this equation is not complete. We have to find some way to get rid of the R1Y. Well, we only had one Euler's equation for this problem. We only had sum of moments about the center of mass. Now, we could do sum of moments about the pin joint, and we are going to later, but that's not going to help us here. If we want to get rid of this, we have to go find another equation to constrain it. So this is where Newton's second law comes in. If we write Newton's second law for this problem, for this body, what we're going to get, minus MAG YN plus R1X, X hat A, plus R1Y, Y hat A. This is going to equal, remember that this is equal to ddt of Ka. Now, that's ddt of Ma VA, and this is going to be Ma VA dot. We have VA dot. We talked about it in the beginning. This is Ma multiplied by L theta double dot Ya minus L theta dot squared Xa. So the equation is your sum of forces equal to mass times your linear acceleration. Remember, what's the point of going here? We want to get an expression for R1y. Notice that we don't actually care about R1x. R1x is important when you're designing the bracket and when you're designing the rod, because it plays into the internal stresses in these components. But just for the dynamics, we just need R1y. Well, here's R1y. Notice that R1y acts in the y hat a direction. What if we took this equation and we did a dot product with the y hat a direction? Not the y hat in direction, but the y hat a direction. So what are we going to do to get that? Let's connect these things. So here we go. This is equal to this. Notice that our accelerations are already in the A frame. The only problem, now we have this this gravity term that is in the the y hat in direction. So what we can do, we can either take all of this body frame stuff and we can put it into the inertial frame, or we could change this inertial frame into the A frame. That's what we're going to do for this one. So I'll tell you what, let me clean just a little bit up, and we'll do that. I've cleaned these up and rewritten them. Here's the Euler's second law equation on top, and then Newton's second law is on bottom. I've gone ahead and I've rotated the y hat in into the A frame. Now, how did I do that? Well, I tend to think of rotations in terms of matrix operators, but consider we have these original definitions of the rotations. We know that this is cosine theta xn, this is sine theta yn minus sine theta xn, and cosine theta yn. What you can do is you can extract these n bases from this system, and we could put these things into a matrix: cosine theta, sine theta, minus sine theta, cosine theta. And of course there's the third row down here, the z's that I'm leaving out as well. But xn, yn. Now what happens when you go in the other direction? What if we want to solve for the xn's in terms of the x and y a's? What happens there is that this matrix between them just becomes a transpose. So I tend to just look at it in terms of columns instead. This becomes x hat in column, and this is the y hat in column. So y hat in is equal to sine theta x hat a cosine theta y hat a. If you get into any kind of more advanced dynamics or kinematics or robotics, anything like that, you'll practice this this rotation back and forth between frames often, and it ends up coming fairly quickly once you get used to it. For now though, there we go, there's the rotation. If we do our dot products, we're going to take Newton's second law, we're going to dot it with y hat a. We're going to have r1y minus mag. The y hat a component is going to be cosine theta. This is going to equal ma L theta double dot. Okay, so clearly we can take this and we can solve for the R1y. Ma L theta double dot plus mag cosine theta. Now, what happens if we take this and we put it back into original equation? That was the point, right? So let's Move this up a little bit. R1y, MAL theta double dot plus MAG cos theta. Okay. Now the original equation, bringing it down, tau minus L times R1y, we have an expression for it, MAL theta double dot plus MAG cosine theta. This is going to equal IZZ theta double dot. Next, we see that there's a theta double dot here on the left-hand side. Let's move that to the right, and we're going to have left over tau minus MAG times L cosine theta. This is going to equal IZZ plus MAL squared, and that multiplied by theta double dot. And there we are. This is finished. This is the equation of motion for this pendulum. How do we know that we're done? Well, this problem had 1 degree of freedom. When we look at this, we have a differential equation for that degree of freedom, for that generalized acceleration. We're going to look at problems, we're going to look at another problem which is 2 degrees of freedom, and in that problem you get 2 differential equations where you can solve for the 2 independent coordinates. So we only have 1 independent acceleration, so we need to solve for it. That's this equation. Everything in this equation is defined. We eliminated that reaction force. Now the torque, this is something that is just external or specified. Maybe this torque is being generated by some controller, or maybe you, the engineer, you're programming it in, so you're just, you would know this value. Mass is known, gravity is known, length. This theta is just your current angle. So as your pendulum moves, clearly the instantaneous value is going to change. And if we wanted to, we could go back and we could replace this IZZ with that other term. You said it was 1 over 12 ml squared. So if we do 1 over 12 MA, and it was 2 times L squared, so that's going to give us 4 L squared, and 4 over 12 makes 1/3. So it's that plus MAL squared. Okay, so that makes it all total 4/3. So this on the right-hand side, this is 4/3 MAL squared. If I did that math right, 1 over 12, 4 1/3. Yeah, okay. All right, so here's our equation of motion. Consider what it took for us to get here. We had to do all the kinematics, we had to do free body diagrams, we have to write the equations, and because we decided to do the sum of moments about the center of mass, that left an unknown reaction force creating a moment about that point. In order to eliminate that reaction force, we had to go back and we had to use the other equations that were available to us, specifically Newton's second law. What if we take the sum of moments about the pin joint though? If we do it correctly, we should get the same answer. So make sure you have this written down, and let's do that next. I've written sum of moments on A about N. Recall that there's only now the external torque generated by the motor, and then the moment created by gravity, pulling it down. The reaction forces no longer appear. We know that Euler's second law, in its final form, it's going to be minus MA, the position vector from A to N, cross Vn dot, plus IAN omega NA dot, plus omega NA cross IAN omega NA. There is a little simplification we can do for this problem. Since we are taking the moments about the pin joint, and that pin joint does not move, then Vn dot, that's going to be 0. So that whole term is gone. And let's next sort out IAN. In the previous method, when we did sum of moments about A, this term went to 0. So let's see if it goes to 0 now. IAN, this is going to come from parallel axis theorem. So what we need is this displacement dyadic. The original matrix, IXX, IYY, IZZ, zeros on the off-diagonal terms, plus, so MA. Now the displacement dyadic from A to N, this is a function of that position. Vector from A to N, and that is negative L in the x hat A direction. So there's only a displacement in the x, no components in the y or z. So this displacement dyadic is going to look like this. L squared 0, 0, L squared. And again, go back to the lessons on parallel axis theorem to see that one in action. And what we're going to get for this modified inertia matrix IAN is IXX, IYY plus MAL squared, and then IZZ plus MAL squared. So there's our IAN matrix. Now, if you take that IAN matrix and you multiply it by omega NA, you cross that with omega NA, you'll see in this case that this one also goes to 0. Because we're doing simple rotations around only the z-axis, when you multiply these two together, you will get that modified inertia matrix times the theta dot in the z, and then you cross it with a vector acting on that same axis and you get 0. So this one's equal to 0. This one is equal to 0. What we are left with now, sum of moments on A about N is going to equal IAN omega NA dot. So let's just take the things we have and let's put them together. The left-hand side is going to be tau minus MAG L cosine theta, and the right-hand side is going to be IZZ plus MAL squared times theta double dot. This is, of course, all still vector. I'm dropping that z hat A notation and I'm just writing the scalar equations. And if you recall, just a moment ago when we finished taking the moments about the center of mass, this is actually the same thing that we got. This is the same equation. So what does that tell us? If you have a problem where it's easier to take moments about the pin joint, you can get the correct answer there as well. It doesn't matter which point you take the moments about. At the end of the day, if you do it correctly, you get the same answer. Now, sometimes it's easier to do it about center of mass. Sometimes, as we saw here, we could actually do it about the pin joint. And notice we didn't have to eliminate any reaction forces. Because we took the moments at the pin joint, the reaction forces never ended up in the moment equation in the first place, but we did have to apply the parallel axis theorem. So ultimately, it's just, you give a little, you take a little. Which one do you think is easier? Personally, I think that this is very simple. I think this approach is much easier and you have to do less work getting rid of the reaction forces. But hey, you're the engineer, it's up to you. Okay, so that's it for this video. We're gonna be making another one soon with pendulums attached to other things. But for now, here you go. There was 1 degree of freedom, so 1 second-order differential equation. All right, best of luck, everyone. I'll see you around.